In Chapter 3, Section 1, we're going to take a look at scatter plots and correlation. So to start off, we want to define correlation. And correlation measures direction and strength of the relationship between two quantitative variables. So when we talk about direction and strength, direction refers to is it positive or negative, and strength refers to is it weak or strong. And we're going to talk more about correlation a little bit later on in the notes. So when we talk about the two variables that our correlation is measuring, one of them is the response variable and one of them is the explanatory variable. So a response variable measures the outcome of a study. So you can think of the response variable as the y value. So we're going to take a look at graphs here in a little bit. And the response variable is the y value. It's the output. So outcome, output, very similar. The explanatory variable either explains or influences the changes in the response variable. So you can think of this as the x value. So if we're relating back to linear equations, the explanatory value is our input, it's our x value, that gives us the response variable, which is the outcome or the output, the y value. And one of the ways we're going to be able to look at the relationship between explanatory and response variables is through a scatter plot. So it displays pairs of quantitative variables. And like I said, one of the variables are one explanatory and one response. So for example, we have a scatter plot telling us the study hours versus your exam score. So your hours studied influences your exam score. And you can have values, because it's a scatter plot, it doesn't have to be a linear equation. It can be multiple values above the same explanatory variable. So like someone who studied 1 hour, someone got a 40 and someone else got a 50. 2 hours, we have what looks like a 60 and 70, 3 hours, 80. So you can have multiple values on top of the same x value. That is okay for a scatter plot. So we're going to take a look at an example. So for centuries, people have associated intelligence with brain size. A recent study used magnetic resonance imaging, so an MRI, to measure the brain size of several individuals. The IQ and brain size in units of 10,000 pixels of 6 individuals are listed below. Is there an explanatory variable? If so, what is it? And what is the response variable? Make a scatter plot of these data. So if I'm trying to figure out my explanatory and my response, I want the one that influences the other. So basically we're saying my brain size, so the larger my brain, the higher my IQ. So the explanatory is going to be the brain size, and the response variable is going to be your IQ. So when we make a scatter plot, along the bottom, I'm going to have my brain size. And on the size, on the side, IQ. So my brain size, if we look, my lowest brain size is 88, the highest is 106. So when I'm trying to think of my scale, I'm gonna start at 80 and go up by 5s. For IQ, the smallest IQ is 80, the largest is 140. I'm going to go up by 10s here. So a brain size of 100 had an IQ of 140. So I go to 100 and 140, place my first value, and then 90 and 90, 95 and 100. Then I had a 92 and a 135, 88 and 80, and lastly 106 and 103. So this is the scatter plot that represents brain size and IQ. So when we're interpreting a scatter plot, they're very easy to create. But we use scatter plots to determine if the two variables are related. So we look for a pattern. So this is where the correlation is going to come into play. So we first look at direction. So variables are positively associated if they move upwards from left to right. So in our scatter plot we just created, as brain size increased, so did IQ. So that is a positive relationship. Negative is if they move downwards from left to right. Then we look for strength. So how strong is the pattern? Do they seem to line up perfectly? And then we look for any deviations or potential outliers that may throw off the overall pattern. So if we're looking at our scatter plot that we made for brain size and IQ, do we notice any patterns or outliers? So I can see a kind of pattern here. So I'm gonna highlight. So it seems to be there's a pattern if we try to get the most value. So those 4 values seem to stick along a pattern. So I would say there are 2 outliers. And the outliers seem to be the 90 or the 88, the 92 and the 135, and then the 100 and the 140. So my 2 outliers seem to be my values at the very top here. They don't seem to follow the overall pattern that I've kind of highlighted in the green. So now is where we're going to tie this back into correlation. So correlation is a statistic. It's a value we represent by the letter R that describes strength and direction of a straight line relationship between 2 quantitative variables. So a linear relationship. So when we talk about correlation, it's a number between -1 to 1. And the strongest correlations, if we're talking about a positive correlation, 1, which means it perfectly follows along a linear relationship. So the closer you are to +1 for a positive relationship, the stronger the correlation. If you have a negative relationship, -1 is the strongest. So the closer you are to -1 for a negative relationship, the stronger. 0 is the worst. 0 practically says there's no relationship between these 2 variables. Anything close to 0 on either side, positive or negative, is considered extremely weak. So a positive correlation is any type of positive number, so between 0 and 1, and then a negative correlation is any sort of negative value between 0 and -1. Correlation does not take into account which is the explanatory and which is the response variable. You have to know which is which. Outliers do affect correlation strongly, And if you change units, it doesn't change the correlation. So if you were going to say, well, I'm going to change what I had in feet to inches, it doesn't change the correlation because the numbers are, the relationship is still going to exist between those numbers. So we're going to take a look at some examples. So our first example here is an example of a pretty positive straight line relationship. And if I look at my graph, if I were to draw a line, most of my values fall within that line. There are a couple outliers, which is why it's not a perfect one. It's a 0.92. But for the most part, it follows the same relationship. We have an example of a negative straight line relationship. So again, R is negative 0.87, which is still pretty strong. We have a few more outliers that make it not as strong as -1, but it's still a pretty strong relationship. Negative 0.87 is still really close to a -1. Then we have a couple examples of nonlinear relationships. So this third example, the R equals negative 0.32. It is negative, but it's not a pretty strong relationship, because if I were to try to draw a linear graph, I would want my linear graph to hit as many values as possible, and there would be a lot of outliers. It wouldn't be the best relationship for these graphs isn't linear, and correlation is going to describe a linear relationship. And then our last example is an example of no relationship at all. We have an R of 0.12, which is pretty close to 0. There's a lot of potential lines I could draw here to try to hit some lines, but not a lot of the points are going to fall on that line. So now we're going to talk about how to calculate correlation coefficient. So we're going to first estimate our correlation coefficient from our brain graph. So if we go back to that graph, I drew a semi-line that hit all but like 2 of my values, but they were huge outliers. So if I'm going to estimate my correlation, it is going to be positive. I'm going to say 0.65. It was, based on the line I drew, it looked like it was pretty strong, but that doesn't mean mathematically it actually is. And that's what we're going to talk about next, is how to actually calculate correlation coefficient. So the formula for correlation coefficient is R equals 1 over n minus 1 times the summation of x minus x bar over sx times y minus y bar over sy. So we need to talk about what these represent. So R obviously represents our correlation coefficient. N is the number of values in your data set. Xi and Yi represent each of those values. So, and we're going to do an example here. So like if we're talking about our brain and IQ, Xi would be our brain size values. Yi would represent all of our IQ values. Okay. X bar and Y bar are the means for your data set. And then Sx and Sy are the standard deviations for each of your data sets. So if we were going to calculate correlation coefficient directly by hand, it would be a very time-consuming process. We would calculate mean by hand, standard deviation by hand, then we'd have to plug it all into the formula. So I'm not going to do it quite all by hand. I am going to use a calculator to calculate the standard deviations and the means for me, but I will show you how to calculate the correlation for our brain IQ by hand partly. So if let's start by listing some of the values. So the mean for our brain, because brain was our explanatory variable, was 95.17. The mean for the IQ is 108. The standard deviation for the brain was 6.77, and the standard deviation for IQ is 24.29. Right off the bat, looking at standard deviations, because the standard deviation for my Y value is so high, I'm already starting to think that the correlation I estimated above is gonna be not as high as I thought because the standard deviation for y is so large. Because remember, standard deviation talks about the spread of data. So because the spread for our y values is so large, that means there are more outliers, which is gonna heavily influence our correlation coefficient. So now I'm gonna set up how we're gonna calculate r. So r equals n minus 1. So n is the number of values. So we had 6 people we looked at, so 6 minus 1. Okay. Now I'm going to start that summation part, the part with the summation. This is where the bulk of the work comes in for correlation if you're not going to do standard deviation by hand. So what I have to do is each x value I have to subtract the mean from it, divide it by the standard deviation, and then multiply it by the corresponding y value minus its mean over the standard deviation. So my first x value was 100 minus the mean 95.17 over the standard deviation, which is 108, multiplied by the corresponding y value. So the first y value, I did that backwards. The standard deviation is 6.77. So multiplied by that corresponding y value, so the first y value is 140 minus the mean 108 over its standard deviation 24.29. So that's the first value. Plus, now I have to move on to the second value for each. So there are going to be 6 numbers here being multiplied. So 90 minus 95.17 over 6.77 times 90 minus 108 over 24.29 plus 95 minus 95.17 over 6.77 times 100 minus 108 over 24.29 plus 92 minus 95.17 over 6.77 times 135 minus 108 over 24.29 plus 88 minus 95.17 over 6.77 times 80 minus 108 over 24.29 plus 106 minus 95.17 over 6.77 times 103 minus 108 over 24.29. So what you want to do now is I used a calculator. I took what's in these brackets and I typed it into a calculator to get the answer. I did not do it by hand. I did not do it one problem at a time, although if that's what's going to work for you, by all means do it. But I used the calculator. I put all of that work in brackets in the calculator. It's extremely important that you're double checking every step, that what you're typing is what you have written down, that it's all correct, because if you make one little error and putting it into the calculator, it's going to affect your entire answer. So once you type that entire thing that's in brackets in the calculator, you should get should get 1.885, and it's actually going to have more decimals, but those are the first two that matter. So we had the 1 over 6 minus 1, and 1 over, that becomes 1 over 5, times the 1.885. So then we end up with r equals 0.377. So our correlation is 0.377. So my estimate of 0.65 was pretty far off. which once I calculated the standard deviation, I kind of knew that that's the way it was headed. The bigger the standard deviations, typically the smaller your correlation is going to be, because that means there's more spread in your data. So if I'm going to look at the relationship between brain size and IQ, it is a positive relationship, which we kind of already knew because they're positive values, but it is also weak. 0.377, not a very large number, not very close to 1. So we can't say that there's no correlation. We can just say there's a weak correlation between your brain size and your IQ. Now, if we had to calculate correlation by hand every time, it would get very, very time consuming, and we don't have the time for that. So what we can actually do is use our graphing calculator. So that's what this last part is, calculating the correlation in your TI calculator. So what you're going to do is you're going into stat and you're going into edit, and under list 1, you're going to put all of your brain sizes. So 100, 90, 95, 92, 88, and 106. Under list 2, you're going to put all of the IQs. So 140, 90, 100, 135, 80, and 103. Okay, now to find the correlation, and then other numbers we're going to use later, we're going to go back into stat, we're going to go use the right arrow to go under calc, and then we want 4, lin reg, and we're going to talk more about that later. So the X list should be L1, the Y list should be L2, then you're going to go down to calculate and hit enter. And it's going to give you a lot of information. It should give you an A, a B, an R squared, and then finally R. And R is what we care about. R is the correlation. And if we look in the calculator, R is 0.377303, keeps on going. So we can see that what we calculated by hand is very close to the exact calculation that the calculator gave us. So we know we have a very accurate correlation between our brain size and IQ. The calculator is going to be our best friend for correlation coefficient, especially if we're checking our work in case you are asked to do it by hand. So we're going to take a look at a couple more examples, and I'm actually going to do these in the calculator instead of by hand, just because it's very time consuming to do larger values by hand. There's 10 countries here, and 6 was pushing it by hand. 10 is a very large amount to do by hand. So we're just going to do this in the calculator. So I'm going to go back into edit, and I'm going to clear out my lists from that previous example. And what we're calculating is the correlation between GDP and life expectancy. So GDP talks about how well off a country is economically based on like the goods they sell. Obviously, life expectancy is the average age of people when they pass away. So our GDP is going to be our X. It's our explanatory. So how well off a country is should influence the life expectancy, because obviously if your country is pretty rich, you're not going to have a lot of people who are not making a lot of money, therefore they're in poverty, and typically people in poverty pass away at an earlier age. So I'm going to put in my values under list 1. So again, it's extremely important that you're double checking that what you put in the calculator matches up with the data you're given, making sure there's no errors, because like I said before, this can influence your value. You'll get something that's incorrect. And then I'm going to put life expectancy, which is our response variable, under L2. Then I'm going to go back to stat, over to calc, and down to 4. And when I hit calculate, we're going to get that R equals 0.809. So if we're talking about what this correlation represents, 0.809 is obviously positive. So basically, as your GDP increases, your life expectancy is going to increase, which you would expect to happen. And then 0.809 is fairly close to 1. So we're going to say that it is also a strong relationship. So we have a positive, strong relationship between GDP and life expectancy. So lastly, we have we want to create a scatter plot for our data and find the correlation of the data set on Excel, which I'm actually going to do it on the calculator here, but I will create a video for you guys to watch with this example for Excel as well. But I'm going to do it on the calculator for now. So we have data that compares study hours to exam score. So if I'm labeling my explanatory and response variables, I'm going to say the study hours are the explanatory. The amount of study hours you study should influence your exam score, Y. So again, I'm going to go into Stat and Edit. I'm going to clear out my lists so I can calculate the correlation. I'm going to type in my study hours and my exam scores. Back to Stat, Calc, and then 4. And in doing so, we're going to get R equals 0.85. And then it's 478, which if we're rounding 3 decimal places becomes 0.855. So this is also a positive relationship, which makes sense. If you study more, the more you study, the higher your exam score should be. And 0.855 is close to 1, so it's also strong. So another positive, strong relationship. So if I'm going to go down here to my scatter plot, I know my explanatory is my study hours, and my response is my exam score. So along the bottom here, if I'm looking at study hours, it looks like I go range from 1 to 7. So I'm going to go from 1 to 8. Then we're going to take a look at our exam scores. So if we look, our lowest exam score is 40, our highest is 100. So I'm just going to go up by tens. And then I'm going to start creating my scatter plot. So we had 2 values for 1 study hour. We had exam scores of 50 and 40. So we had 40 and 50. For 2 hours, I'm going to put little check marks knowing that I use them. For 2 hours, we had 75 and 65. We had 1 3 at an exam score of 80. We didn't have a 4. We had a 5 at 90. We had a 6 at 80. and then we had 3 7s, a 90, an 85, and a 100. So 100, 90, 85. So I'm looking at my scatter plot and I'm comparing it to my correlation R. I can see that if I were to try to draw a linear relationship for this, most of those values are pretty close to that line. And we're going to take more closer look at these linear relationships in the next section and how a line is created that best matches our data and our correlation. Make sure you check out the video on how to create a scatter plot on Excel.